Right, reminders again, okay, unit exam for Unit 4 is tomorrow. And guys, my room is not affected by any of the diploma exams, so you can come straight here. Okay? You don't have to worry, we're not displaced. I am the end of normalcy at the end of this hallway. Okay? Everybody else has to be abnormal. But not me, I get to be normal. And reminder that your final exam, Friday, January 24th, 9 a.m., be here for the regular start of school. Okay, look on the board outside the gym, find out what rows you're in, come in, it's alphabetical order from there. Okay, find your test, sit down, all that good stuff. Okay, remember, you have fresh batteries or freshly charged calculator, pencils, lots of them. Okay, snack, drink if you need it, and obviously don't bring your phone. You heard that this morning, and you'll hear it every day. Okay, through exams. Don't bring your phone, don't bring your smartwatch, okay, any of that stuff. Don't bring your data sheet, you're getting a fresh one for the final. Okay? Now, in terms of final exam review here for Unit 2, okay, there actually weren't that many concepts in Unit 2, but the concepts themselves were pretty detailed and pretty broad. Okay? So we started out in Unit 2 with Newton's first law, which is pretty simple. Okay? There's not even really any math to do with it. Newton's first law is inertia. It is the behavior of an object that is not experiencing any net force. Okay? If an object is not experiencing any net force, it will exhibit one of two behaviors. What are they? It'll stand still or travel at a constant velocity. A net force is required for an acceleration to occur. That's Newton's first law. Okay? Newton's second law deals with when that net force is present. Okay, so we have to remember that net force can be calculated in two ways. It is the vector sum of all the forces acting on an object, so it's often handy to draw a free body diagram. Then, if necessary, a vector diagram. Okay, and that net force can also be calculated by multiplying the mass of the object by the acceleration that it is experiencing. Okay, that's Newton's second law, but that was the one that was very broad in terms of a topic. We went over a whole bunch of different applications of Newton's second law, and today I have a whole bunch of kind of practice, typical exam kind of items for you to try that will deal with that concept. When we were done with Newton's second law, we talked about Newton's third law. Okay, every action has an equal and opposite reaction. Okay, we did some problems associated with that. Okay, nothing terribly difficult there. And then we moved on to work energy theorem, okay, which was basically all review of Science 10, except that you could possibly have both potential and kinetic energy changing at the same time. Okay, we did some questions where something is accelerated up a ramp or it's sliding down a ramp and there's friction present and the initial energy and the final energy are different. Okay? If the initial energy and the final energy are different, then there's a change in energy, and that's what work is. Okay? We still used force times distance as well. Okay? It played a part in there, okay? And we solved problems related to that. And then we finished off the unit with the law of conservation of energy, which was no different than what you learned in Science 10. We did, roller coaster problems, things going down a hill, a car jumping off a cliff, okay? Stuff like that, right? And simple stuff there, nothing you hadn't already done before lots of times. Okay? That's what's in the unit, is those concepts. Newton's three laws, work energy theorem, and the law of conservation of energy. Okay? And of course we used the law of conservation of energy quite recently with simple harmonic motion as well. All right, so to give you an idea, okay, here is a typical, let's say, vector involved Newton's second law problem. Right? So you have a 60 kilogram box being pulled by two ropes along a frictionless surface. Rope number 1 pulls due east with 200 newtons worth of force, and rope 2 pulls 50 degrees north of east with 300 newtons worth of force. What is the acceleration of the box? Okay, so reminder, Newton's second law question, free body diagram, vector diagram if necessary, spoiler alert, it is. Okay, so tail to head stuff, and then F equals M times A. Okay? All right, I'll give you a few minutes to try that one. So first thing is, okay, we draw our free body diagram. So we got a 60 kilogram box Okay, there's a 200 Newton force that is due east. And there's a 300 Newton force that is acting 50 degrees north of east. So, okay, so to scale, 300 newtons, and we'll say that that's 50 degrees there. So that's what it's going to look like, okay, for a free body diagram. Now, obviously from there, I can't just add the forces together. They're not collinear. Okay, so what I'm going to have to do is draw a vector diagram on that. So I'll have my 200 Newton force going like this, and then I will have my 300 Newton force. So here's due east. I'm going to go 50 degrees north of that, right, for 300 newtons. All right, so the triangle is going to look like that for that one. And then my resultant will look like this. Right? And my resultant is the net force, and I will, of course, want the angle that is acting at. So that's what my vector diagram should look like. And then, like any other vector question, I've got to find out all of my x's and y's. So blue x is 200 newtons, okay? Because it's just going east, and that would make blue y 0 newtons. Right? So that part's pretty straightforward. For the green one, it's got a triangle, okay? So here's x and here's y. So to calculate those, I've got to do a little trig. X is adjacent, so the cos of 50 times 300 newtons will give me the northerly component of that. Sorry, I just forgot to turn my calculator on earlier. So we will have the cos of 50 times 300, and so that side is going to be 192.8. I'm going to keep all those decimals, obviously, newtons, and that is north. Okay, I actually should have directions on these as well. That is east. Okay, and then for y, it's the opposite side, so the sine of 50 times 300. All right, so that's going to be 229.81. Okay, newtons, and that is going to be east. All right, so now that I've got those sides, okay, so this is the 192 and this is the 229. Now I can do, I can find my resultants, x, so that is how much does that line go over, and my resultants y, how much does it go up? Okay, so resultant x, so red x, is going to be pretty straightforward. It only, it goes 200 and then it goes 192, so 392.8 newtons, and that will be east. Okay, and then for the y component, that's even easier because we only go north in green y, so it's just going to be 229.81 newtons north. Okay, now I've got the two sides of that triangle. I do what I always do with any vector addition. I'm going to do Pythagorean theorem to get the magnitude of the net force. So 229.8 squared plus 392.8 squared give me my net force. Now I'm going to use all of the decimals here, so just got to do that number. Okay, plus 200. Okay, so now I'm going to go with that. So that one squared plus that one squared, okay, is going to give me the magnitude of the net force, 455.12 newtons. Then I've got to get the vector, the way I drew the triangle. Okay, y is the opposite side, so 229 divided by 392. Okay, obviously with all the decimals. that'll give me my angle. So second tan of 229 divided by the 392. Okay, it's going to give me 30.33 degrees north of east. Okay, and now I have to find the acceleration because that's what the question wanted. Right, so F net, so I've already done the sum of all forces, vector sum of all forces part. Now I'm doing the F net equals m times a part. All right, so to get the acceleration, it's F net divided by m. So 455 divided by 60 kilograms. Okay, is going to give me 7 point, we only have what, 2 significant digits here, so 7.6 meters per second squared at 30 degrees north of east. Okay, so we do have to remember acceleration and net force always share a vector because one causes the other. Okay, questions on that one? Okay, feasible to get one like that on the unit exam, or the final exam, sorry? Okay, makes you do vector addition and Newton's second law in one question. Yeah, I'd say so. Okay, what did we call these ones? Started with, these were static, right? Because it's not moving. In any static question, what's the net force? It's 0. The object's not moving, therefore there's no acceleration. Okay, so in this situation, the net force is 0. That means the forces pulling down have to be balanced by the forces pulling up. The forces pulling right have to be balanced by the forces pulling left. Okay, so I want the tension in cable 1. Okay, this will be cable 2 over here, and this angle we'll say is 110 degrees. All right, mass is 100 kilograms, angle between the cables is 110 degrees. Calculate the tension in cable 1. This is also a vector related question. I'll just turn it back on now that these don't look silly. Okay, so 490.5 divided by, as Clay pointed out, the cos of 55, because I don't even understand my own labeling. Okay, 855 newtons. Okay, would be our correct tension in the cable. All right, okay, and that should be cos up there and cos up there. All right, questions on that one? So some vector stuff, but that's a net force is 0 situation. Okay, this would be what kind of a question? I've got a mass at the bottom of the ramp and it's being pushed up the ramp, right? The force being used to push it along and up the ramp is 500 newtons. Ramp is 20 meters long. When it gets to the top, it's 10 meters higher than it was at the bottom. What kind of question is this? This is a work energy theorem question, exactly. Okay, the energy at the bottom is going to be different from the energy at the top. Okay, and I have a force and a distance. Okay, the length of the ramp would be the distance over which this force is applied. All right, see if you guys can figure that one out. Okay, work is a change in energy. How do I know that this is a work energy theorem question and not a conservation of energy question? Because you're given force. Exactly. You're never given force when the initial energy and the final energy are equal, because forces do work. They change the energy. All right, so this has to be a work energy theorem question simply on that regard. Okay, so if I push something up a ramp, it's got to gain some energy. It's going to have more at the top than it has at the bottom. So here's what I need to do. I need to understand that work is a change in mechanical energy. Okay, one of the ways to calculate work is force times distance, and I have that. Okay, they tell me it's 500 newtons and it's exerted over 20 meters, the length of the ramp. Right? The energy is going to change, so I'm going to have the final mechanical energy minus the initial mechanical energy. Okay? Now, how do I normally calculate mechanical energy? What do we add together? The kinetic and the potential. All right, so if I'm looking at this situation here, I'm going to have force times distance equals, okay, EK final plus EP final minus EP initial minus, or sorry, plus EK initial. Are any of those zero? EP initial, yeah, we're at the bottom of the ramp. We wouldn't have any potential energy there, okay? Everything else is likely not zero, right? I'm probably going to be accelerating this thing up the ramp, so it's gonna have kinetic energy at the top. It's definitely gonna have potential energy at the top. So now, okay, I need to look at how do I get what I need by itself. I'm trying to find the speed of the object up here. That would be part of the final kinetic energy. So I need to isolate that. What's the first thing I should move? Yeah, I should move this over to here, right? I should add the initial kinetic energy over to this side. So I'll have force times distance. In other words, the change in energy plus my initial energy equals my final energy. EKF plus EPF. Now, not in brackets because I don't need brackets anymore. Okay, what do I do with the final potential? Subtract it over to the other side. So what I'll have is force times distance plus EK initial minus EP final should equal my final kinetic. All right, now I got to plug my numbers in. All right, so I'm going to have force times distance plus 1/2 mvi squared minus mghf equals 1/2 mvf squared. Can I get vf by itself now? Yeah. Okay, divide both sides by 1/2 of m and square root. Okay, so fair amount of algebra here, but the concept's fairly straightforward. 500 newtons times 20 meters plus 1/2 times, what was the mass, 100 kilograms, 8 times 3 squared, minus 100 times 9.81 times 10 meters, divided by 1/2 times 100. Right? That should give me my final speed. All right, so 500 times 20 plus 0.5 times 100 times 3 squared, okay, minus 100 times 9.81 times 10, okay, divided by 50, square rooted. All right, so at the top of the ramp, it's going to be moving at 20 meters per second. Okay, is that faster than the bottom? That's because I gave it energy, right? I did work in pushing it up the ramp. Okay, so you guys are looking at that like I made a mistake. Did I make a mistake?
You did plus 100 times.
Oh!
9.8.
Did I say plus or did I say minus? Did I just push the wrong button?
Yeah.
Pretty sure I said minus. Okay, sorry, let's try that again. This number here,
Wrong.
it did seem kind of fast. I mean, it should be a little faster, but probably not that fast. Okay, minus 100 times 9.81 times 10. Okay, and then divide that by 50. Okay, and then square root that. Okay, so a little tiny bit faster than it was at the bottom. That's a little more reasonable. Okay, everybody all right with that? Okay, so work energy theorem problems. Okay, work's a change in energy. Force times distance equals the change in energy. Manipulate and solve. Okay.
So that last question,
Yep.
does it matter if you do it like you find the net force?
If you want to do it as a Newton's second law question, you can.
I just did it to make sure I had the right answer,
Yep.
but I was just like, I got the same answer. So.
You will get the same answer, but there are more steps and more chance to make a mistake. But yeah, absolutely you can. Yeah. Okay. All right. So here I've got a 200 kilogram block sitting on a 30-degree incline, and it is accelerating down the ramp at 1.7 meters per second squared. I would like to know the force of friction acting on the box. As you know, inclined planes are my favorite kind of inclined plane question, or Newton's second law question. Of course, inclined planes are my favorite inclined plane question. That's sort of like by default. But it's my favorite kind of Newton's second law question. So, give that one a try. Let's see what we remember about inclined planes and Newton's second law. If the box is sliding down the ramp, which way is friction acting? Up the ramp. Okay, so I can put the force of friction on here. That's what I'm trying to solve for. Okay. I know that the acceleration is 1.7 meters per second squared. Okay, what are the other forces acting on the box? Well, in any inclined plane, gravity is pulling the box straight down. Okay, so this is going to be 1,962 newtons worth of gravitational force, is 200 times 9.81. Okay, then if I've got that, the force of the ramp pushing back would be this side. That would be F normal. I don't need that. But those two things combined produce a vector sum that is this special force that we really do need, F parallel. Okay? And the way that they're related is through the angle of the incline. So now that I've got that right angle triangle drawn, can I find the amount of force that is parallel to the plane downwards? Okay, I just have to use sine because it's the opposite side to the one that I have, or to the angle, and I have the hypotenuse. Okay, so I'm going to go sine of 30. Actually, it's going to be 981 because it's sine of 30. Okay, so opposite side, this is going to be 981 newtons. Okay, so this is going to be 981 newtons. Okay. Those are the only two forces acting up or down the ramp, that is within the plane of the movement. All right, so does that mean then that effectively the vector sum of all forces will be F parallel plus the force of friction? It does, because F parallel is already the vector sum of gravity and normal force. Okay, so all I have to do then is isolate FF. So I'm going to take F net minus F parallel, and that'll equal the force of friction. Now, F net, I have to calculate by going m times a, right, and then subtract my 981 newtons, and that'll give me the force of friction. So mass times acceleration, 200 times 1.7 should give me, what, 340? Okay, 340 newtons minus 981 newtons. These are both down the ramp, so I'm making them both positive. But when I do this, I get a negative number. Is that okay? Yeah, because if I made down the ramp positive, then my force of friction should be negative because it's up the ramp. 81. Okay, negative 641 newtons. All right, so that makes sense. It's less than F parallel. That's why the object is sliding down the ramp. This only has two significant digits, so my force of friction would be 6.4? Yeah, 6.4 times 10 to the 2 newtons up the ramp. How important is that vector? Depends whether you want 5 out of 5 or not. If you only want 4 out of 5, don't write up the ramp. Okay, it's a vector quantity, so it should have a vector on it. Okay, ringing a bell? Okay, these are a lot of the things that we did in Unit 2. Okay, there's a system question for you. Okay, there's a 2 kilogram mass sitting on a level surface. There's a force of friction resisting it of 4.0 newtons. There is a 0.750 kilogram mass hanging over the pulley. I would like the acceleration of this mass. Okay, I want the acceleration of the 0.750 kilogram mass. Okay, let's have a look at this one. So it's a system. Do all the parts have to accelerate at the same rate? Same direction? No. Same rate, same magnitude, but not the same direction. So what I'm first going to do is I'm going to calculate the forces involved. I already have the 4 newtons worth of friction, but I do need this force, which is the force of gravity. So mass times gravity, 0.75 times 9.81 is going to give me 7.3575 newtons. Okay, now I'm going to simplify this thing. The net force is acting on the entire system, not just one part of it. So I'm going to draw a combined mass of 2.75 kilograms, okay, and I'm going to have it being acted upon by 7.3575 newtons that way, and 4 newtons this way. And I calculate my net force. I mean, I've simplified the diagram, but essentially this is what's going on, right? So my net force, the vector sum of all the forces, is going to be 3.3575 newtons, okay, in that direction, which is not really a direction it's moving, but we'll say it is for now. Right? Now I should be able to calculate the acceleration by going F net over m. So just force net is m times a. Now when I do this, here's the part people forget. 3.3575. I want the acceleration of the 0.750 kilogram mass. What mass do I use here? 2.750, the combined mass of the system, because that way I'm calculating how quickly the whole system accelerates. That's what rate everything accelerates at. So this is divided by 2.75. Okay, little trick there that could be involved in something on the test. So 3.3575, okay, divided by 2.75. Not times, divided by. All right, 1.22 meters per second squared. Down, because I am asking about the mass that is falling. All right, everybody okay with that? Okay, so important to know the rules of systems, important to know the rules of inclined planes, okay? You know, they could be questions that show up there, maybe even in combination, okay? But it doesn't change kind of what you do. Okay. What kind of question is this? This thing is sitting on a frictionless hill. It's got a mass of 10 kilograms, initially moving at 4 meters per second. A little while later, it's at a height of 10 meters, moving at 16 meters per second. I want its initial height. Yep, this one is, yeah. So if there are no forces mentioned, then the initial energy and the final energy are going to be equal because no work is being done. All right, so in that way, we can identify it as a conservation of mechanical energy question. All right, so now what I'm looking at here is that the initial potential plus the initial kinetic is going to equal the final potential plus the final kinetic. So much like the work energy theorem question we did before, okay, calculating mechanical energy means adding those two types together. What I'm looking for is the initial height. So that's going to be part of this term. So I'll isolate it right now by subtracting the initial kinetic over to the other side. So I'll have the initial potential equals the final potential plus the final kinetic minus the initial kinetic. All right, now that I've got that, now I can put in my formulas. So m times g times h initial equals m times g times h final plus 1/2 mv final squared minus 1/2 mv initial squared. M's will cancel. Okay, they're in every term. You don't have to cancel them. I gave you the mass. You could have plugged it in for every one, but you'll get the same answer. Right? I just need to isolate hi, so I'm going to divide both sides by g, bring it over here, and then I'm just plugging in my numbers. 9.81 times 10 plus 1/2 times 16 squared minus 1/2 times 4 squared divided by 9.81. Okay, so 98.1 plus 0.5 times 16 squared minus 0.5 times 4 squared. Okay, divide that by 9.81. All right, so the initial height of that hill or ramp or whatever it is 22 meters. We have two significant digits. Okay, ringing a bell? All right, so really any of those could be game for a question on the final. Okay, some of them could be combined with concepts from other units, like the vector question we did at the beginning. This could be in this form, or it could be in a form from Unit 4 where the potential energy is elastic. It's the same concept either way. But yeah, that's the kinds of things that you're going to encounter, okay, from this unit. Okay, any questions from you guys that you would like to go over from Unit 2? But,
I wasn't
okay. Okay, you can use the rest of the class to prepare. You've got that final exam review package or the unit exam review for tomorrow. For tomorrow, if you want, you can come in here at, let's say, about 5 after 12. If you want to start a little bit early and get a little extra time, that's totally fine. Come in then and you can get started. And then obviously on Thursday, we'll go over this exam and do any stuff on circular motion and gravitation that we can get to, okay, for the final exam review there. All right, that's the plan. We got 2 days left, guys. All right, so let's use the rest of the class here effectively. And if you have questions, I'm happy to answer them. Okay, but let's get to work. Yes.